Good morning. I trust you are well and blessed. Today we are going to do the heat module. Okay. So I'm going to share my screen. The heat module is broken down into 4 main topics. Where am I? It's broken down into 4 main topics. So it's the specific heat capacity and heat transfer. That's the first topic. Then the heat value of fuels, then expansion, as well as steam. So for this lesson, we're going to look at the topic, the specific heat capacity and heat transfer. On completion of the topic, you should be able to define specific heat capacity, briefly explain why it is, why the heat capacity of substances differ and what is the meaning of the specific heat capacity of a substance, and explain the significance of the high specific heat capacities of water. I won't really go into the theory. We covered that in N1 and N2. I will focus mostly on solving problems. Then we're also going to look at the law of conservation of energy as applied to heat, and then apply that in calculations. So first and foremost, what is heat? Heat is a form of energy. It is measured in joules. So the joules will indicate how much heat energy a body has. And then temperature determines the degree of heat. It tells us how intense is the heat in the body. So it doesn't tell us the amount of heat, but it tells us the heat intensity or the degree of heat. So temperature is measured in degrees Celsius or kelvins. You should be able to convert from degrees Celsius to kelvins and vice versa. Okay. Then what is specific heat capacity? It's the amount of heat energy required to raise the temperature of 1 kilogram of a substance by 1 degree. Okay, so we have different specific heat capacities for substances. Because you only take 1 kilogram of a substance and you raise its temperature by 1 degree. So you can measure how much heat energy you used to do that. And because that is a specific amount, 1 kilogram and 1 degree. So you can always say that the specific heat capacity of this substance is this amount. So this is just an example. The specific heat capacity of water is 4187. So if you look at this table, which is the information sheet that you're gonna get when you do your finals, the specific heat capacities are given somewhere here at the bottom. You've got the one of steam, of water, aluminium, oil, steel, or copper. So this means it takes 390 joules of heat energy to raise the temperature of 1 kilogram of copper by 1 degree. That is what it means. And then there are 3 factors that will determine how much heat energy a body can absorb or release. Those factors are mass, specific heat capacity, and change in temperature. They led us to this formula. Q is mc delta T since N1. Now, let's just take a closer look at this formula. If we look at mass, mass must be measured in kilograms, but just remember for water, 1 liter equals to 1 kilogram. And that is because the density of water is 1,000 kilograms per cubic meters. So if you do all the calculation, it will bring you to that conclusion that 1 liter is 1 kilograms. However, for other substances, if they give you the volume, then you must multiply that volume with the density to get the mass. So the densities of specific substances are also given here. You've got the density of aluminium, density of gold, of alcohol, of mercury, of platinum, of water, of oil, mineral oil, of air. So they just need to mention what substance it is, and then you come and you get the density from this page. Okay, so the specific heat capacity is a constant value is given on that page. Then the change in temperature, just remember if water boils, we assume that it boils at 100 degrees Celsius. So for my calculations, I just name T1 as the initial temperature and T2 as the final temperature. So your change in temperature. So remember, we're looking at this formula. Q is MC delta T. So we spoke about mass, that it must be in kilograms. If they give you volume, you must use the formula to calculate mass. Then specific heat capacity, you get it from the page, and then change in temperature. We're now busy discussing change in temperature. So change in temperature is higher temperature minus lower temperature. So if T1 is higher than T2, the change in temperature will say T1 minus T2. But when T2 is higher than T1, your change in temperature will say T2 minus T1. Okay, so that's all when it comes to this formula, the MC delta T. Then how is heat energy conserved? We know that heat flows from a warmer substance into a cooler substance until both are at the same temperature, meaning the heat that is lost by the warm body is gained by the cool body. So that is how heat energy is conserved. If they say there are no heat losses, it means the amount that is released is the same as the amount that is absorbed. So the MC delta T of the hot substance will be the same as the MC delta T of the cool substance. Okay, so mostly at N3, you will be given 2 or 3 substances. The syllabus does mention here that you can expect to apply the law of conservation of energy in calculations concerning mixtures consisting of not more than 3 substances. Okay, so it can be 2 or 3 substances. So let's look at an example. So as you read the question, once you identify that you have 2 or more, I would suggest that you open up a table to record your givens. Open up a table to record your givens, such so that you don't mix them up. So let's look at this example. It says a piece of steel with a mass of 21 kilograms at a temperature of 89 degrees Celsius is immersed in 5 liters of water at 17 degrees Celsius. Then the question says, calculate the final temperature of the water if no heat is lost. So my suggestion is that you open up a table to record your givens. So you have steel here and you have water. So it says a piece of steel has a mass of 21 kilograms. So that is the mass of steel, 21 kilograms. And that is at 89 degrees. That is the initial temperature of steel. It's initially at 89 degrees Celsius. It is immersed in 5 liters of water. That is the mass of water. Remember, we said for water, 1 kilogram equals to 1 liter. And this water is initially at 17 degrees Celsius. Okay. So yeah, even though T2 is not given, you can see that the steel is hot and is put into water to cool it down. So the T2 of steel is going to be less compared to the T1. Therefore, the change in temperature will say higher temperature minus lower temperature. But in this case, the water is receiving heat energy from the steel. So the T2 of the water is going to be higher than the T1. Therefore, the change in temperature of the water is going to say T2 minus T1. So this side is T1 minus T2. That side is T2 minus T1. Then the other thing you need to get is the specific heat capacity. The one of water is 4187 joules per kilogram degrees Celsius. You get it from this page. I just know it by heart because we work with it so much, the one of water. So here's the specific heat capacity of water. Then the one of steel is there, is 500. So the specific heat capacity of steel is 500 joules per kilogram degrees Celsius. Okay. So let's calculate. These two are sharing heat energy, so that means the Q of the steel will be the same as the Q of the water. The MC delta T of the steel will be the same as the MC delta T of the water. Okay, then we can substitute. But let's first expand the formula. MC, the delta T of the steel is going to be T1 minus T2. We're looking for T2. And then the delta C of the delta T of the water is gonna be, we worked it out already there, T2 minus T1. Okay. So what is the mass of steel? Is 21. The C of steel is 500. The T1 is 89. The T2 is what we're looking for. This side, the mass of water is 5. The C of water is 4187. The T2 is what we're looking for. The T1 is 17. Okay. You can work with it as is, but in my case, I just prefer to work in kilojoules, because if you work in kilojoules, then your values are not so large. Then it's manageable. Okay. So to do that, I will change this to kilograms, 0.5 kilograms, and that one is kilojoules, and that one is 4.187. Okay, so I've basically just changed this one to kilojoules, 0.5 kilojoules, and that one 4.187 kilojoules. That's all I've done. Okay. And then let's do the mathematics. So this side we have 21 times by 0.5. It gives us 10.5. So it's minus 10.5 T2. So you just do your math, your own method. Multiplied by 89. It gives me 934.5. This side, I have 5 times by 4.187. It gives me 20.935. 20.935 T2 minus this answer times 17. That gives me 355.895. Okay. So what I'm going to do, I'm going to bring like terms to the same side. I'm going to take 10.5 and add it to 20, because it's going to come this side and become positive. So it's 20.935 plus 10.5. It gives me 31.435 T2. And then I take this over to this side, and then it becomes positive. It adds to 934.5. This value plus that value, 355.895. So it becomes 1290.395 divided by 31.435 divided by 31.435. So T2 becomes 41.05 degrees Celsius. So that is how you calculate your temperature when you have substances that are mixing. You want to know the temperature of the mixture. All right, thank you.